These problems kind of extend and apply in a different way the problems we saw previously. So here we're thinking about it in terms of a graph that represents our particle motion. So the axis here could be number of particles, could be particle density, could be lots of different things, but it is a measure of how many particles have a certain property. And then here it would be velocity or speed of those particles, usually in meters per second. Lots of different units here. So the farther right we go, that means faster moving particles. The taller we go, that's more particles with that speed. So an important thing, whether we're looking at the same element at different temperatures or different elements, is the area under the curve in total represents all of our particles. So if we have equal moles like we do in this scenario, a narrow but tall peak would have the same area under it as a wider but shorter peak. We're not going to see two that are the same height, and we're not going to see two that are the same width unless we're changing the number of particles there. So then we're thinking about nitrogen and xenon. They're at room temperature, so both at the same speed, meaning same average kinetic energy, equal moles. It doesn't specifically say anything about pressure or volume, but although it's the same flask it's the same flask, which implies same volume and same pressure. There we go. So with the same average kinetic energy or same temperature, that means same average kinetic energy, the more massive xenon have to be moving slower. So the peak right here, which is taller, is showing me that most of my particles have a speed right around here in the 400 meters per second range. Although nitrogen spread out and we have fewer particles moving at that speed, we have way more particles moving at 600, 900, 1200, and 1600. Our kind of average here is about 800 meters per second. So the more massive particle has a peak farther to the left, where more of the particles are moving more slowly, and the lighter of the particles would be further to the right. We could calculate exactly how much different that is, but that's not what we're asked to do here. Thinking of this same scenario and then just looking at all the different possible variables, pressure, we've got the same particles moving with the same average kinetic energy in the same container, meaning the same force of collisions. Particle speed, we just graphed, it's different. But once again, if we have to explain this in words rather than a graph, we define same temperature, same average kinetic energy. We refer to the kinetic energy equation, including mass and velocity, which explains why different velocities are required if the masses are different. It defined as the same number of particles. We've got an equal number of moles, equal particles. We've said the same temperature, which means same average kinetic energy. And then here, kind of the new thing, and my lights, I'm losing my lights. It's a little bit creepy because it's early in the morning here. Rate of effusion is how quickly would they escape a small hole in a container. So we poke a pin into a balloon, or basically the idea of effusion is that we are limiting the direction that that gas can move. Even if we're in like a small tube, a straw or a demo that we might look at would be two gases traveling through a tube there where there's really only one direction that they can go. They move at different speeds. We've defined that. So they effuse or spread out at different speeds. So different masses have different speeds at that same temperature. Xenon is heavier. It will move more slowly than nitrogen. And we could even look at the masses to specifically see this different rate. It is an inverse square relationship in terms of mass and rate of effusion. It is not something that we would likely have to do a calculation on, but it is something we could do a good estimation on how much faster one thing would be than another. With our molar masses of 133, the square root of that around 12, a molar mass of nitrogen of 28, the square root of that's around 6. So nitrogen would effuse about twice as fast. Obviously, lots of rounding in my numbers there, but it gets me close enough to know that even though it's a 28 to 131 ratio in terms of square root, it's closer to a 2 to 1 ratio in terms of the rate of effusion and therefore the speed that they travel.